In the last video, at the end of the last video, there was a connection problem, so it was cut off abruptly. This is going to be a continuation of Math 219, lecture 15, part 1. We were considering example 2. The example was, let me remind you, to solve the differential equation, second derivative of y plus 3 times the first derivative of y plus 2y equal to cosine t, and we obtained the general solution of the corresponding homogeneous equation as C1 e to the minus t plus C2 e to the minus 2t. And since the function bt on the right side is cosine t, and derivative of cosine t is sine t, and the second derivative is again in terms of cosine t, so we guess the form of the particular solution to be some coefficient a times cosine t plus another coefficient b times sine t. Now, to find the coefficients a and b, to find a and b, we plug this yp into the equation. So in order to do this, I need to find the first derivative and second derivative of this function, yp. So when yp is a times cosine t plus b times sine t, the first derivative is minus a times sine t plus b times cosine t. And the second derivative, minus a times cosine t minus b times sine t. So when we plug it into the equation, we need to figure out the second derivative of yp plus 3 times the first derivative plus 2 times the function. So second derivative is minus a cosine t minus b sine t plus 3 times the first derivative is minus a sine t plus b cosine t. And then we have 2 times the function itself, a times cosine t plus b times sine t. And if we simplify this expression, how many cosines do we have? We have minus a here, minus 3a, so the sum is minus 2a. Oh, sorry, I'm looking at cosine, so let's do this. I have minus a from the first term, and plus 3b from the second term, and plus 2a from the last term, cosine t, plus, how about sine t? Minus b from the first term, minus 3a from the second term, plus 2b from the last term. So this is a plus 3b times cosine t plus b minus 3a times sine t. So this is the left side of my differential equation, and this should be equal to cosine t. So that means the coefficient a plus 3b should be equal to 1, and the coefficient b minus 3a should be equal to 0, because there is no term with sine t on the right side. So the coefficient of sine t should be 0. So we need to solve this system of equations to find the numbers a and b. From the second equation, I have b equals 3a. And if I substitute this into the first equation, I have 4a equals 1. So a is 1 over 4. And since b is 3a, b is 3 over 4. So this means our particular solution is 1 over 4 times cosine t plus 3 over 4 times sine t. So let me check my own solution to see if I did this right. Okay. Oops. B equals. Oh, I'm sorry. Yes. So B is 3a. When I substituted it into the first equation, I don't get 4a, but I get 10a equal to 1. So a is 1 over 10. B is 3 over 10. So my particular solution, 1 over 10 times cosine t plus 3 over 10 times sine t. Okay, so that's my particular solution. Of course, you can always check your answer. Once you find your particular solution, you can go through the steps of finding the derivatives and plugging it into the equation and see whether it really satisfies the differential equation. So then our general solution, remember, general solution of the homogeneous plus particular solution. So C1 e to the minus t plus C2 e to the minus 2t plus 1 over 10 cosine t plus 3 over 10 sine t. Okay. So again, the general procedure, maybe let's consider the general procedure again. First, we consider the homogeneous equation. So we set the left side of the equation equal to 0. And then we find the general solution of the homogeneous equation. We call it y sub h. This h maybe, not y sub h, yes. Then we guess by considering the function bt and its derivatives, we guess the general form of the particular solution. And then we take the derivatives of that form, plug it into the equation to find the constants, the coefficients. And then we form the general solution by taking the general solution of the homogeneous equation plus our particular solution. Okay, so now let me consider another example, example 3. The question is the same, solve the equation. Second derivative of y minus y equal to e to the t. Okay, so again, same steps. First, the homogeneous equation. Second derivative of y minus y equal to 0. And for the homogeneous equation, we write the characteristic equation. Lambda squared minus 1 equal to 0. So lambda is plus or minus 1. So that means the general solution of the homogeneous equation is C1 e to the t plus C2 e to the minus t. For lambda equals plus 1, we have e to the t, and for lambda equals minus 1, we have e to the minus t. So we take a linear combination to get the general solution of the homogeneous equation. our function b of t is e to the t, and all derivatives of bt is, again, e to the t. So we guess the particular solution to be some multiple of e to the t. But we have a problem here now, because e to the t is also a part of the general solution of the homogeneous equation. The function e to the t is a solution of the homogeneous equation. So when we plug it into y double prime minus y equals e to the t, we get yp double prime minus yp equal to 0, not e to the t. Okay, so this equation, this is equation, homogeneous equation. Okay, so that means the function, any multiple of e to the t cannot be a solution of the original equation. So what do we do in this case? We make a second guess. What we do is, instead of taking just e to the t, we multiply it with t. This is inspired by the case of repeated roots. Remember, if we have a repeated root, first we take the function e to the lambda t for that root, and for the second solution, we multiply that solution with t. So we have e to the lambda t and t e to the lambda t. So here, we guess that it might also work in this case, since e to the t is a solution of the homogeneous equation. For the non-homogeneous equation, we multiply e to the t with t. So let's see if this is going to work out. In this case, what is going to be the first derivative? Now, a is constant. We have the product t times e to the t. So to find the derivative, we need use the product rule. Derivative of t is 1 times e to the t plus t times derivative of e to the t is, again, e to the t. So what is the second derivative? Again, a is constant. Derivative of e to the t is e to the t. Plus derivative for t times e to the t, again, I use the product rule. Derivative of t is 1 times e to the t plus t times derivative of e to the t is, again, e to the t. So the second derivative is the constant a times 2e to the t plus t e to the t. So when we plug it into the equation, the second derivative of y minus the function, second derivative is a times 2e to the t plus t e to the t minus the function itself, a t e to the t. So you see, in this case, the term with t e to the t cancels out. A times t e to the t minus a times t e to the t. So we get only 2a times e to the t. You see what happens. When you multiply e to the t with t, when you take the derivatives, you get an extra e to the t. If you just consider the function e to the t, the first derivative and the second derivative will be, again, e to the t. But when we multiply it with t, in the second derivative, we obtain an extra e to the t. So this makes it possible for this expression to be equal to e to the t. So for this to be equal to e to the t, a should be 1/2. So our particular solution then 1/2 t e to the t. So the general solution, remember, general solution of the homogeneous equation plus the particular solution. So C1 times e to the t plus C2 times e to the minus t and plus the particular solution 1/2 t e to the t. So let me repeat in this case, not in this case, but in general, in this example, let me point out that in the particular solution, we don't have any constants. The particular solution is just one solution of the equation, so there are no constants involved. The constants come from the general solution of the homogeneous equation, because for the homogeneous equation, we have the principle of superposition. So once we get two solutions, any linear combination is also a solution, but that's only for homogeneous. The principle of superposition doesn't work for non-homogeneous. So the particular solution doesn't have any constants, just the particular solution you figure out using the method of undetermined coefficients or by some other method. Remember, we also have, we are going to discuss it in the next video. We also have the method of variation of parameters. So when your function bt on the right side, so let me write what we did differently in this example. When bt and or derivatives of bt is a solution of the homogeneous equation, we multiply by t. All right. But the thing is, when you multiply by t, it may still be a solution of the homogeneous equation. In this case, I will do this in the next example. In this case, you multiply with another t. So you keep multiplying by t until you get rid of all solutions of the homogeneous equation. So this is going to be the case in the next example, example 4. Let's solve the equation. Second derivative of y minus 4 times the first derivative of y plus 4 times y equal to t times e to the 2t. So we consider the homogeneous equation. Second derivative of y plus 4 minus 4 times the first derivative plus 4y equal to 0. And then we write the characteristic equation. Lambda squared minus 4 lambda plus 4 equal to 0. But this expression we can factor out as lambda minus 2 squared equal to 0. So lambda equals 2 is a double root. In this case, the general solution, C1 times e to the 2t, because we obtained solution lambda equals 2. So we have the function e to the 2t plus C2 times, now we multiply e to the 2t by t. So the homogeneous equation has the general solution, C1 e to the 2t plus C2 times t e to the 2t. Now, the function bt is t e to the 2t. So when you take derivatives, since bt is a product, t times e to the 2t, in the derivatives, you will get two kinds of functions, t times e to the 2t, or just the exponential part when you take the derivative of t. So derivatives, all derivatives are a linear combinations of t e to the 2t and e to the 2t. So we guess the particular solution to be a coefficient a times t e to the 2t plus a coefficient b times e to the 2t. But in this combination, t e to the 2t and e to the 2t are solutions of the homogeneous equation. So again, when we plug this into the differential equation, we are going to get 0. So as we did in the previous example, for the second guess, multiply by t. So we make a second guess for the particular solution, a t squared e to the 2t plus b times t e to the 2t. So we multiply the whole thing, the whole form of the general solution with t. But still, we have a problem. The first term is fine, t squared e to the t, but t e to the 2t is again a solution of homogeneous equation. So we make another guess for the third guess. Multiply by t again. So our third guess is a, the constant a, times t cubed e to the 2t plus b times t squared e to the 2t. And now we are fine because neither function, this should work. Since both functions t cubed e to the 2t and t squared e to the 2t are not solutions of the homogeneous equation. So we take this form for the particular solution, and again, by taking the derivatives, we take the derivatives, plug it into the differential equation, and we find the coefficients a and b. This part, in this example, is going to be a little bit long compared to the previous examples, but it is straightforward. You just take derivatives, you combine like terms, and you plug it into the differential equation, you compute the left side, and then make it equal to the right side, t times e to the 2t, and using the coefficients, you get your equations for a and b, and then solve them to find a and b. So let's do this computation. So let me write the general form of yp again here. A t cubed e to the 2t plus b t squared e to the 2t. And let's remember the original equation. What is our equation? Oops, I don't have enough space here. Y prime, y double prime minus 4y prime plus 4y equal to t e to the 2 e to the t e to the 2t. Oh my God. Okay. Let me check my equation here. Yes. I see that I make a mistake here. This should be the second derivative of y. Yes. So second derivative minus 4 times the first derivative plus 4y equals 2 t e to the 2t. All right. So we take the first derivative of this particular solution, a times product rule. Derivative of t cubed is 3t squared e to the 2t plus derivative of e to the 2t is 2 times, but we also have the function t cubed, plus b times derivative of t squared is 2t e to the 2t plus derivative of e to the 2t, so 2 t squared e to the 2t. And what I'm going to do, I'm going to combine the like terms. I have two terms with t squared e to the 2t. So in the first term, the coefficient is 3a, plus in the second term, it is 2b times t squared e to the 2t. And then we have 2a t cubed e to the 2t plus 2b t e to the 2t. So that's our first derivative. For the second derivative, we take the derivative of the first derivative. So 3a plus 2b is constant. Derivative of t squared is 2t e to the 2t plus derivative of e to the 2t is 2 times e to the 2t plus 2a times derivative of the t cubed is 3t squared, and derivative of e to the 2t is 2 e to the 2t plus 2b times derivative of t is 1 plus derivative of e to the 2t is 2 e to the 2t. So again, we combine the like terms. So first t e to the 2t, I have another one right here. So if you combine the coefficients, I have 3a plus 2b in the first term, and from the last term, I get 2 times 2b, so I get 4b. So the coefficient is 3a plus 6b. No, okay. This is in here in the first term, we also have the number 2. So, okay, let's do this right. But what we can do is both of them are 2t. So when we add the coefficients, 3a plus 4b, but we also have the 2 coming 2 in front of t. So we have 2 times 3a plus 4b t e to the 2t plus. Now t squared, we have a term here and a term here. So in the first term, the coefficient of t squared is 2, and in the second term is 3. So let's be careful. If I multiply by 2 in the first term, I get 6a plus 4b. And from the second term, multiply 2a with 3, we have plus 6a, t squared e to the 2t. And then we have just one term with t cubed plus 4a t cubed e to the 2t, and then 2b e to the 2t. So 6a plus 8b t e to the 2t plus 12a plus 4b t squared e to the 2t plus 4a t cubed e to the 2t plus 2b e to the 2t. I think I made a mistake. Okay, where did what did I do wrong? Okay, because, okay, why do I think that I made a mistake? We have only 2 coefficients, a and b. So we need only 2 equations to solve for a and b. That means I obtained 4 terms here, but I should have obtained only 2 terms. So 2 of the coefficients should have been 0, so that I have only 2 terms left, and I can write the 2 equations to find my constants a and b. So let me check. Okay, the first derivative is 2a t cubed e to the 2t. Okay, 3a plus 2b t squared e to the 2t. Yes. Oh, I'm sorry. This is only the second derivative. I didn't plug it into the equation yet. I'm sorry. So let me check my second derivative. 4at cubed e to the 2t plus 12a plus 4b t squared. Yes. 6a plus 8b t e to the 2t plus where am I 2b. Yes, okay, I'm sorry, I didn't plug it into the equation yet. This is just the second derivative. After we plug it into the equation, on the left side we should have only 2 terms left, so that we have only 2 equations for the constants a and b. So let's be careful. For the left side of our equation, I need to compute the second derivative of yp minus 4 times the first derivative plus 4 times the function yp itself. So the second derivative, 6a plus 8b t e to the 2t plus 12a plus 4b t squared e to the 2t plus 4a t cubed e to the 2t plus 2b e to the 2t minus 4 times the first derivative. The first derivative comes from here, 3a plus 2b t squared e to the 2t plus 2a t cubed e to the 2t plus 2bt e to the 2t, plus 4 times the function itself, a t cubed e to the 2t, plus b t squared e to the 2t. Okay, so first the term t e to the 2t. I have a term here, another term here. That's it. Okay, so here the coefficient in the first term, 6a plus 8b, and in the second term I have 2b, but remember it's multiplied by minus 4, so minus 8b t e to the 2t. And then t squared I have here, here, and here. Okay, so from the first one, we have 12a plus 4b. From the second one, I have, wait a minute. From the second one, I have 3a plus 2b times minus 4. So minus 4 times 3a plus 2b. And from the last one, I have 4b. T squared e to the 2t. Now with t cubed here, here, and here. So 4a plus, no, minus, because in the second term I have 2a, but it's multiplied by minus 4. So minus 8a. And from the last term, I have 4a. T cubed e to the 2t. And the remaining ones are for e to the t. From the first one, I have 2b. From the second one, in the second one, there is no e to the 2t, and in the last one, either. So we have only one term left, plus 2b e to the 2t. Okay, so the first one, 8b minus 8b is 0, so 6a t e to the 2t. Next one, 12a minus 12a is 0, 4b minus 8b, so minus 4b plus 4b 0, so the second term vanishes. You see the coefficient of the second term is 0. And the coefficient of the third term is also 0, and we have the last term, 2b e to the 2t. And this should be equal to t e to the 2t. So the coefficient of t e to the 2t, which is 6a, should be equal to 1, and the coefficient of e to the t, which is 2b, should be 0. So that means the number a is 1 over 6, and the number b is 0. So our particular solution then is 1 over 6 t cubed e to the 2t. Number b is 0, so we don't have the term with t squared e to the 2t. And the general solution, remember, is the homogeneous solution plus the particular solution. For the homogeneous, we have, for the homogeneous, what was the homogeneous equation? The solution is C1 e to the 2t plus C2 t e to the 2t, and we add the particular solution, 1 over 6 t cubed e to the 2t. Again, let me point out, in the particular solution, there are no constants c, 3, or whatever. It's just one solution with one coefficient, 1 over 6. We don't multiply it or add a constant, okay? Just 1 over 6. So this is the general solution. As I said, the computations are a little bit long, but it is straightforward. So you keep multiplying by t until you are free of any solution of the homogeneous equation. Okay, so next time we consider the method of variation of parameters. That's all for now.